So hi, I'm Vasilis Trigonakis, and in this talk I will present almost everything you wanted to know about synchronization. This is a joint work with Tudor David and Professor Rashid Gerari at PFL. So unless you have been hiding in the desert, you have heard about the multi-core revolution. So this means that nowadays in pretty much every device, let it be a mobile, a laptop or a PC, or of course a server, we have a multi-core processor. And as you all know, multi-cores brought very big challenges in the design both of hardware and of software. And in software, one of the biggest challenges is the need for scalability. In other words, we want applications that can increase their performance as we increase the number of cores that they execute on. So as you also know, one of the biggest bottlenecks in scalability is synchronization. Synchronization is the coordination of accesses to some shared data or some shared resources in general. And unfortunately, it cannot always be avoided because not all applications are embarrassingly parallel. So synchronization is just an overhead in our application. So it doesn't really add to the real computation of the application, but it is there just for correctness. And therefore, scalability of synchronization can be defined as the ability of a primitive to not degrade its performance as we increase the number of cores. So for instance, we would ideally like a lock to have the same latency to acquire, regardless of how many threads share this lock. This is really important because if we increase the number of threads, and at the same time we increase the cost of synchronization, we then decrease the performance and the scalability of our applications. So what we know for sure is that the scalability of synchronization is really important for the application scalability. What we further know is that synchronization is a really difficult problem. This can be illustrated by the huge amount of work in the past decades, both on designing, implementing, and evaluating new synchronization primitives and schemes, and on trying to fix synchronization-related bottlenecks in systems and applications. Actually, if I wanted to be thorough and fair on the references I provide on this topic, then I would probably need to fill a bunch of slides. In any case, regardless of the huge amount of work, if we nowadays face some scalability problems due to synchronization in an application, it's not immediately clear to figure out where do these problems come from. So is it the underlying hardware? Is it the use of specific atomic operation? Is it the synchronization primitives that are being used? Or is it the application or the workload that executes on top of this application? So what this indicates is that there is a somehow limited understanding of the behavior of synchronization on real hardware. And because of this, we decided to take a step back and perform a thorough analysis of synchronization on modern hardware in order to try to answer to the question, what is the main source of scalability problems in synchronization? To spoil it for you, our results indicated that the scalability of synchronization is mainly a property of the underlying hardware, in the sense that even if you have some reasonable software solutions, it is still the hardware that mainly determines the scalability trends that can be achieved. In more details, we first confirmed and quantified the conventional wisdom that crossing sockets is a killer for the scalability of synchronization. We measured that just transferring one cache line of data from one socket to another is up to 8 times more expensive than sharing the data within a socket. Since synchronization has to build on top of these latencies, it's immediately clear that we want to minimize cross-socket synchronization as much as possible. However, we further showed that even sharing within a socket is necessary for achieving scalability, but it's not sufficient because your hardware might still induce cross-socket traffic under the hood, even if you explicitly put all sharing in software within a socket. Then, regarding intra-socket uniformity, so uniformity on single-socket processors, we saw that it's an important property and that a uniform cache architecture can actually scale quite better than a non-uniform, even with the slightest degree of non-uniformity. We then measured the latencies of load, store, and atomic operations and showed that on x86 machines, if the data are not locally cached and you actually need to fetch them from a remote cache, then a load and a store can be almost as expensive as an atomic operation, and therefore we should not always blame the use of atomic operations for all our scalability problems. Now, these 4 observations are actually attributes of the underlying hardware, and therefore they cannot be really bypassed by the software. We saw how this manifests on lock algorithms, and partially explains our last observation that simple locks are powerful. In the paper, you can find more observations that I will not describe in this talk due to the sake of time. So, before I continue, I want to clarify that we do not claim that badly designed synchronization can scale well due to the underlying hardware, but we do claim that even if you have well-designed synchronization, you might not get the scalability you would expect due to the underlying hardware. So now that we have seen the high-level conclusions of this work, let's see the methodology we took and the experiments we performed in order to reach to these conclusions. So we tried to be as pragmatic and as thorough as possible in this study, and therefore we considered two dimensions: the potential hardware platforms and the different layers of synchronization. First, regarding our target platforms, we tried to consider a representative set of processors, and this consists of two multi-socket processors, an 8-socket 48-core AMD Opteron, and an 8-socket 80-core Intel Xeon, and two single-socket processors, the Sun UltraSpark T2, also known as the Niagara 2, that is an 8-core processor with a total of 64 hardware threads, and the Tylera Tile JX36, that is a 36-cores processor. Then we dissected synchronization into 4 layers, where the 2 bottom layers is actually synchronization implemented in hardware. There we have the cache-coherence protocol that provide the load and store operations to our applications. And on top of that, we have the atomic operations layer, where we have the atomic operations such as concurrent swap. On the 2 upper layers, we have synchronization in software, where we have the software primitives that implement synchronization, such as lock-based or message passing-based synchronization. And on top, we, of course, have the systems and applications that make use of the software primitives in order to design and implement the synchronization patterns of the application. So in the rest of this talk, I'll go through our observations one by one, and I will present experiments that illustrate their correctness. So let's start with why do we say that crossing sockets is a killer for the scalability of synchronization, and how did we quantify this? To illustrate this point, we first measured the load, store, and atomic operation latencies depending on the distance of the requesting core to the data. And on the Opteron, we measured that within a socket, you can communicate, 2 cores can communicate in approximately 40 nanoseconds. Then, once you cross the borders of a socket, you have an overhead of approximately 40 nanoseconds per interconnect hop. So in the end, over 2 hops, you have a communication latency that is up to 3 times more expensive than communicating within a socket. On the Xeon, within a socket, we measure that you can communicate in 20 to 40 nanoseconds, depending on the previous state of the cache line. And then you have an overhead of approximately 50 nanoseconds per interconnect hop. So in the end, over 2 hops, you have a communication latency that is up to 8 times more expensive than staying within a socket. So overall, we observe that crossing sockets leads to up to 8 times more expensive communication than staying within a socket. And since synchronization is all about transferring context, so transferring data across threads, we can already claim that crossing sockets is a killer for the scalability of synchronization. So let's move on to the primitives layer, and more precisely, to lock-based synchronization. So the results I will present here were taken with a simple lock micro benchmark, where we initialize a number of locks and a number of threads, and then each thread repeatedly selects one of the locks at random, acquires a lock, reads and writes some data that are protected by this lock, and then releases a lock. We repeat this experiment with 9 state-of-the-art lock algorithms, spanning from simple spin locks to queue-based locks, NUMA-aware hierarchical locks, and of course the pthread mutexes. And we report the best performance that can be achieved by any of these locks. So in a sense, our lock-based experiments are the best you can get using lock-based synchronization. So let's see the results, and first focus on the results of the Xeon. So we can observe that when we cross the borders of a socket on this experiment, we see a very steep decrease in the performance of the experiment, which means that we not only get scalability, but we actually get pretty big negative scalability, so a decrease in performance. So, of course, this suggests that crossing socket is a killer for the scalability of synchronization. However, if we look at the results of the Optron, they do not follow the exact same trends when it comes to crossing sockets with the results on the Xeon. And I will explain the reason behind this in a few slides. So let's move on to the application layer, and more precisely, a concurrent hash table. So our hash table is a pretty standard concurrent hash table with per-bucket locking, and the experiment that I will present here contains 20% update operations and 80% read-only operations. So if we see the results, and again first focus on the results of the Xeon, we observe that on high contention, when we cross sockets, we get a very big decrease in the performance of the hash table, so a big negative scalability. While on low contention, we can see that when we cross sockets, the hash table pretty much stops scaling, so we don't get any real performance benefits. Of course, these results, again, verify that crossing sockets is a killer for the scalability of synchronization. As before, as with the logs, on this workload, the Optron does not behave in the exact same way as the Xeon when it comes to crossing sockets, and this will be the topic of my next few slides. So I will now explain the behavior of the Optron on our experiments that will at the same time lead to our second observation that sharing within a socket is necessary for achieving scalability, but it's not a sufficient solution, so it doesn't always guarantee scalability. To better understand the results, I will first present in a high level how do these multi-sockets implement coherence. So on the Optron, there is an incomplete directory that tries to keep track of the different copies of the cache lines, while on the Xeon there are no directory facilities. So whenever there is a cross-socket communication, cross-socket synchronization, then we have a broadcast of requests to all other sockets in order to locate the data. So let's see how these two approaches correspond to locality within a socket. As we saw before, on the Optron within a socket, we can communicate in approximately 40 nanoseconds, while on the Xeon, we have a communication latency of 20 to 40 nanoseconds. So if we now put some data within a socket and a request for this data from a core of the same socket, on the Optron, the directory might be able to point to the data, and in this case, we get the 40 nanoseconds latency that we would expect. But it might also happen that the directory does not have enough information to locate the data. And in this case, we might have a broadcast of requests to all other sockets, only to figure out in the end that the only copies of the cache line reside at the same socket as the request. And in this case, of course, we get the 3 times more expensive communication latency than what we would normally expect. So this might happen on the Optron because the directory can keep track of a single copy of the cache line. So if, for instance, we have a shared cache line, the directory will keep track of only a single copy of this line, and therefore it cannot locate all the different copies. On the Xeon, the inclusive last level cache is always able to detect whether there is sharing only within a socket, and therefore we always get the 20 to 40 nanoseconds latency that we would expect. So what these results illustrate that even trying to optimize for inter-socket sharing is necessary because we might get the low inter-socket latencies. But it's not a sufficient solution to achieve scalability because your hardware might provide you with the expensive cross-socket latencies in any case. So let's use these results to explain the behavior of the Optron on logs. So there are 2 main things to observe on these graphs. First, that on the Optron for high contention, when we cross sockets, we do not get the steep decrease in the performance that we get on the Xeon, while for low contention, we get some sort of scalability even when we cross sockets. This can be partially explained by the fact that the penalties when we cross sockets on the Optron are lower than the penalties on the Xeon. The second point that is even more important is that even within a socket, and even for low contention on the Optron, we do not get any performance increase. So we don't get any scalability even within the socket. This immediately leads to our second observation that sharing within a socket is not sufficient for achieving scalability, which means that even if you optimize for inter-socket sharing, it doesn't mean that you will necessarily get scalability. On the hash table, the situation is pretty similar with the logs. And we notice that on high contention, again, we don't get a very steep decrease in performance on the Optron when we cross sockets, while on low contention, we again get some sort of scalability. If we notice the behavior of the opteron within a socket, we can again see that even for low contention, we get very limited scalability compared to what we get on the Xeon. And this again confirms that sharing within a socket is necessary because it is a good optimization for getting scalability, but it's not sufficient because it doesn't guarantee that we can get scalability. So let's now move on and see how our single socket processors behave in terms of synchronization. So, as I said before, we measure the core-to-core communication latencies in our systems, and on the Niagara, we actually have a uniform latency of approximately 23 nanoseconds due to the shared crossbar and the equidistant last level cache. While on the Tylera, because of the network on chip, we again have non-uniformity, and we measure that two adjacent cores can communicate in approximately 40 nanoseconds, and then we have an overhead of 2 nanoseconds per network hop. So in the end, we have the two most remote cores can communicate with 50% more expensive latencies than two adjacent cores. We actually expect that the uniformity of the Niagara will lead to higher scalability than the non-uniformity of the Tylera. And let's see how this appears on our experiments. So first on logs, and the first thing to observe is that on both the Niagara and the Tylera, on both the contention levels, we get very nice scalability on this experiment. However, if we look at the precise numbers, the 3.8 maximum scalability on high contention on the Niagara compared to the 2.3 maximum scalability on the Tylera is 70% more, while the 25x maximum scalability of the Niagara compared to the 21.2 maximum scalability on the Tylera is approximately 20% more for low contention. So overall, we observed that, indeed, the uniformity of the Niagara provided better scalability, higher scalability, and actually it led to up to 70% higher scalability on the logs experiment. On the hash table, the situation is pretty similar, and both on high and on low contention, we observed that the uniformity of the Niagara led to higher scalability. More precisely, in this case, we observed that the uniformity led to up to 50% higher scalability, thus confirming that intra-socket uniformity is an important property. So let's now see the latencies of load stores and atomic operations on our multi-sockets. And first see these latencies when the data are locally cached in the L1 cache of the requesting core. So in this case, you can immediately observe that a concurrent swap is significantly more expensive than a load or a store on both Opteron and Xeon. And actually, a concurrent swap in this case is an order of magnitude more expensive than a load and a store. However, if the data are not locally cached, and we actually need to fetch the data from a remote cache, so a remote core, in order to complete the operation, then we observe that a load and a store again have a similar behavior. But even more interestingly, a concurrent swap has also very similar latencies to loads and stores. And in numbers, on the Opteron, a concurrent swap is up to 35% more expensive than a load, while on the Xeon it is up to 12% more expensive. So overall, we observe that loads and stores can be almost as expensive as atomic operations when you need to fetch the data from a remote cache. This means that we should not consider the use of atomic operations as a root of all evil for the scalability of synchronization, because a store can potentially have the same effects as a concurrent swap in our scalability. So even if you have some reasonable software solutions, it might still be the hardware that mainly determines the scalability trends that can be achieved. Let's see how this manifests on logs, and leads to our last observation that simple log algorithms are powerful. So on this slide, I have put together the experiments on the hash table on all 4 platforms. And additionally, on top of each bar, I have plotted which is the best log algorithm at each data point. Without going into the details of the results, if we observe which log achieves the best performance in each case, in most scenarios, and actually in 25 out of the 32 cases, it is simple spin logs that performed the best, thus verifying that simple log algorithms are powerful. So I want to clarify that you should take this result with a grain of salt, because we don't say that simple log algorithms are suitable for every workload. we just say that simple locks seem to be sufficient in most scenarios, especially if you take into account the observations that I described before. So to recap, we saw why crossing sockets is a killer for the scalability of synchronization, since it leads to up to 8 times more expensive communication latencies. We then saw that even if you try to optimize for intra-socket sharing, your hardware might still induce cross-socket traffic under the hood and ruin your expected benefits of locality, and therefore sharing within a socket is necessary but not sufficient for achieving scalability. We then saw that intra-socket uniformity is an important property and can lead to higher scalability than even the slightest non-uniformity, and then that loads and stores can be almost as expensive as atomic operations when you actually need to transfer the data from a remote core. So this means that we shouldn't blame the use of atomic ops for all our scalability problems. So finally, we saw how these attributes of the hardware can actually affect the synchronization in software by presenting that simple lock algorithms are pretty powerful. Overall, the big picture of our results is that scalability of synchronization is mainly a property of the underlying hardware. And we believe that knowing the low-level details of your hardware is the only way to achieve the best out of your synchronization. In the paper, you can find more observations, more supporting results, and additionally, how can you leverage these results to optimize synchronization and avoid potential scalability bottlenecks. I have just a couple of slides before I conclude. And the first would be that in the beginning of the talk, I told you that I would present almost everything you wanted to know about synchronization. I use the word almost because we obviously did not analyze all the hardware platforms out there, but we tried to consider a representative set of processors. And additionally, there are more ways of implementing synchronization in software, such as lock-free data structures and combiner-based approaches, that we also did not have the chance to evaluate. The last two are actually really good candidates for our future work. So just to say that to perform this analysis, we developed the SSYNC synchronization suite that's available online and contains tools and libraries that can help you analyze the different layers of synchronization on different hardware. With this, I'll finish my talk. Thank you for your attention, and I will be glad to answer to any questions you might have.
As before, I'll start with the moderator question. Does your analysis point to any interesting direction for new improved hardware-level synchronization support in next-generation multi-many-core processors?
So yeah, that's an interesting question. So first of all, we already started seeing the first implementations of TSX, Intel's extensions. And this is definitely something interesting to see. But our results kind of indicate that it could be interesting to have something like hardware locks implemented with the support of the hardware at least. Because with transactional memory, for instance, you might end up under high contention doing more work than what you would do when you are pessimistic. If you have support for hardware locks, then you can optimize your critical sections using the hardware. So I guess this is an interesting direction.
Okay, there's a bunch more questions here. What is a short-term stopgap one could apply to modern processors on commodity hardware? For example, in your experience, does CPU pinning of threads and processors help at all? Should we bypass the current OS schedulers?
So yeah, in the paper we clarify this. So we always pin our threads to cores when we execute the experiments. So when we say that we put everything within a socket, all threads on this experiment execute on the same socket, right? So we observe pretty big benefits when you pin threads on cores. So I can show you a backup slide on this. So you can get pretty big benefits. So on the hash table, for instance, we executed the same experiment without pinning the logs, and we see that you can get like 30% lower performance on the Opteron, for instance. On the logs experiment, this can be actually even higher. Okay, I have many backup slides.
I'll ask a question.
Okay. So this is a logs experiment when we explicitly put everything within a socket and when we let the operating system do the scheduling. And as you can see, I mean, okay, this only stresses synchronization, but you can see that the benefits of staying within a socket are really big on the Xeon and a bit smaller on the Opteron due to the locality problems I described.
Andrew Bauman, MSR. So your high-level takeaway from this was that the scalability of synchronization is basically a property of the hardware. I was trying to think of a way in which the application workload could affect that. Did you ever see latencies increase due to contention on the interconnect? For example, if the application sharing pattern is causing a lot of traffic on the interconnect, maybe you would get an increase in the inter-socket latency.
So we didn't really observe this in our results because they are mainly synchronization bound. So this means that you will have, let's say, pretty big pauses, and you will fetch one cache line for the lock, and that's it. You will execute. I mean, you don't have big chunks of memory going around different sockets, so you don't stress the interconnect. But this can definitely happen. So, and this might introduce queuing in your request for cache-coherence, and it can also affect scalability.
Okay. There's no more from the floor. I'll just do one more from the moderator. Nice paper and talk. Your focus seems to be hardware-based locking schemes, but sometimes OS support, e.g. Linux, Futexes, and Solaris Park Unpark can be useful. Have you done much investigation besides perhaps using pthread mutexes along these lines?
So not really. So we only use the pthread mutexes, and our results indicate that when you pin threads to a core, so when you don't have a sharing of a core by a thread, you don't get, pthread mutexes are slow compared to other techniques. But we didn't investigate something like this more, so just pthread mutexes.
Petros Maniatis, Intel. So I have a more methodological question for your conclusions. The fourth one was about how compare and swap atomic operations and load stores basically are as bad as you wouldn't expect. I find that counterintuitively intuitive. What you're describing is that if I'm doing compare and swap and I have to do a remote load and store, then they scale equally as poorly. That sounds obvious. Am I missing some insight there? Is there something where you disentangle the compare and swap from the load and store and you see that they're as bad? Or are you giving a tautology here? I'm missing the surprising aspect of this.
Okay, so our point is that we want to prevent people from just saying, you know, I will remove this atomic operation and I fixed my problems, right? The actual problem is the request for ownership for the cache line. So this is what we wanted to say to the audience. Maybe it's very clear to some people, maybe it's not that clear for other people.
I'm a synchronization civilian, so maybe I should have known this. Thank you.
Hello. Actually, I may ask a stupid question because I'm a little confused. The first talk in the morning. I'm Yu Xia from Shanghai Jiao Tong University. And the first talk in the morning told us that what matters is actually the API definition. So if we have a commutable API, we can actually doesn't care about the implementation. And your talk told me that what matters is hardware, actually. So I really like to hear your comments on the first work. Thank you.
No, that's a really nice question. Actually, it's completely true. So if you access different cache lines, the only problems you might get is what the previous question asked, bandwidth problems, right? So if you are able to cache your data locally and do your operations, you can get linear scalability, no problem, just bandwidth problems might appear. So what the first talk suggested is actually in line with what we say. But once you start having actual sharing of cache line in read-write mode, then you start having problems. So our results agree with these results, but present how you should implement things, let's say. So you cannot always have commutativity in the end, right?
Yeah, okay, fine, thank you.
Okay, thank you.
Thank you. Thank you.